In today's action-packed installment of Organic Chemistry, we'll be plunging into part 3 of our never-ending series on carbonyl compounds, the compounds that you love to hate. Many years ago, while I was attending Skyview High School in northern Utah as a lad, my friends and I worked diligently to invent substitute cuss words and phrases that might seem sufficiently tasteful to use in more public settings. I'm ashamed to admit that we never really succeeded. One of those phrases was the phrase, Hershey squirts. Thus, when I would stub my toe back over my mom's garbage can with the car or randomly trip on landmines as a high schooler, rather than use a more vulgar tirade of profanities and expletives, I would regularly yell the phrase, Hershey squirts! For some reason, my friends and I eventually began adding or rolling our R's while using that phrase, thinking that it might make it sound more exotic, like Scottish or something. It wasn't uncommon then in my high school to hear one of us yell from down the hallway, Hershey squirts! I don't think it really actually made it sound more exotic, it just made it sound even more stupid. Well, as we approach our third and final installment on carbonyl compounds, you may feel tempted to release numerous expletives. If you feel that temptation, and accordingly wish to, I give you full permission to use the same phrase to which my friends and I recurred back in our youth, Hershey squirts. By the end of this chapter, you should be able to do the following. Explain why alpha hydrogens are so acidic. Explain keto-enol tautomerism. Explain how to use LDA to form enolates. Explain how enolates and enols react. And know the products, reaction conditions, and mechanisms of this list of reactions. Before we go any further, however, I want to introduce you to alpha hydrogens. And what is an alpha hydrogen, you may ask? Well, an alpha hydrogen is a hydrogen that's bonded to an alpha carbon. An alpha carbon is a carbon that's immediately adjacent to a carbonyl carbon. So you can see that shown pretty clearly in this figure here. As you already know, carbonyl compounds exist in two different interconverting forms. The keto form over here and the enol form shown over here. The process of interconversion is called tautomerism, and as you should also already know, the keto form is the major one. Thus, ketone compounds like this one are naturally interconverting between their keto tautomer and their enol tautomer, with the keto being much more prevalent in solution. Since I'm sure you're all wondering, much like a child wonders where babies come from or why the IRS exists, here's the mechanism for keto-enol tautomerism. I'm not going to talk you through it, but I'll let you examine it on your own. I do, however, wish to point out one important aspect of this mechanism, and that is the word enol. You should note that the enol tautomerism is called an enol because it contains both an alkene and an alcohol. So if we look at this, you'll see a carbon-carbon double bond, an alkene, and an OH. That's an alcohol OH. Someone some time ago decided to take the word alkene and the word alcohol and squish them together into one word called enol. So that's where that word arises. I suspect that someday a similar thing might occur when Payless Shoe Source merges with Werther's original caramel company to make a new candy dispensing shoe conglomerate called Worthless Shoe Source. This leads us to our next question. What is an enolate? An enolate is nothing more than an enol that has a negative charge. This results from a base removing the alpha hydrogen. If I remove the alpha hydrogen, have a negative charge on the alpha carbon, you'll note that I could draw two resonance structures here, one shown here and the other with a double bond being between these two carbons and the negative charge being thrust up onto the oxygen. This kind of compound is called an enolate. Now, alpha hydrogens are much more acidic than typical hydrogens bonded to sp3 hybridized carbons. Why, you may ask? Well, I'm going to tell you. Let's analyze this by looking at another one of my magical animated drawings. If we have a hydrogen bound to a typical sp3 hybridized carbon, as is found in methane, shown here, and a base removes that hydrogen, you'll notice that the conjugate base is this negative charged species, with the negative charge being localized on that carbon. What is the pK of this hydrogen? Well, it's around 65. To put that in perspective, if you had 10 to the 65 molecules of methane, and I want you to keep in mind how huge of a number 10 to the 65 is, only one single molecule of that group would exist naturally in equilibrium in this deprotonated negatively charged form. Now, by comparison, if I have a carbonyl compound like this, and a base removes the alpha hydrogen, it gives me this enolate. You will note, as we mentioned earlier, that this enolate is in resonance with this form here. What does that mean? Well, it means that this negative charge is not localized on this carbon alone. It's actually being spread by a resonance between this carbon and this oxygen up here. What does that mean about that negative charge? Well, it means that this negative charge is much more stable than the negative charge up here on the deprotonated methane. This negative charge here is stabilized because of resonance, thus being shared by two different atoms. How does that translate into the acidity of an alpha hydrogen? Well, the alpha hydrogen in a carbonyl containing compound is much more acidic than a hydrogen on methane, making the pKa of an alpha hydrogen somewhere between 17 and 20. To add perspective, we could say that an alpha hydrogen is 10 to the 45 times more acidic than a hydrogen bonded to a typical sp3 hybridized carbon. Why? Because of this resonance stabilization of the conjugate base. Now, the bulk of this chapter will center heavily on reactions of this type of enolate species, so I want you to have it at the forefront of your minds as we continue. Now I'm going to introduce you to this compound, LDA, which is short for lithium diisopropyl amide. I think that's a hilarious name because it's not actually an amide, it's an amine. LDA is a useful base for removing alpha hydrogens to form enolates. How does it do this? Well, as we've discussed in the past, anytime you see an atom like this, lithium, or one of its brethren that's in the first column of the periodic table, potassium or sodium, we see one of these atoms, lithium, potassium, or sodium, bound to an atom that's found toward the right end of the periodic table. We know that this is an ionic bond, so we can effectively treat this compound as if there were a negative charge on the nitrogen. So if I have the negative charge on the nitrogen, and it's staring at a carbonyl compound like this one, what's going to happen? Well, of course, that negatively charged nitrogen is going to strip one of those alpha hydrogens, dumping the electrons into the alpha carbon to give me this enolate. This then converts this negatively charged nitrogen species into this product, diisopropyl amine. This is how LDA removes alpha hydrogens. Let's compare the basicity of LDA with that of hydroxide. If I have a carbonyl compound like cyclohexanone shown here, and I react that with hydroxide, you will note that there might be some minor removal of one of these alpha hydrogens by the hydroxide ion. So let's pretend this hydroxide removes an alpha hydrogen, gives me this enolate, which is of course exists in these two resonance structures. You'll note that when that hydroxide removes the hydrogen from this alpha position, it then becomes water, which is the conjugate acid of the hydroxide. Now, I want to tell you guys that this reaction proceeds almost doesn't proceed hardly at all. In other words, this enolate is only going to exist in less than 0.1% concentration. Why? Well, the reason has to do with pKa. you'll look at water here and see that the pKa of the protons in water is 15.7. The pKa of an alpha proton in cyclohexanone is 17. So what does that mean? Well, it means that the protons in water are actually more acidic than the alpha proton on cyclohexanone. So what that means is that even if I were able to transiently form a small amount of this enolate, it would actually tear a proton off of water and revert back to the starting materials much more prevalently than the starting materials would be deprotonated to form this enolate. Once again, all because this product, water, is much more acidic than the alpha proton over here in the starting material. Let's compare that with LDA. Once again, the pKa of the alpha proton here in cyclohexanone is 17. When LDA strips that alpha proton, it is converted into diisopropyl amine. The pKa of the diisopropyl amine is 35. That means that diisopropyl amine is much, much, much less acidic than the alpha proton over here in cyclohexanone. Hence, this enolate is not going to be able to rip off a proton from diisopropyl amine and revert back to the starting material. Thus, if I incubate cyclohexanone with LDA, it will convert to this enolate in almost 100% conversion. Now, enolates can react in one of two different ways. One way under basic conditions, and another under acidic conditions. Under basic conditions, the base strips the alpha hydrogen here to generate this enolate, which is of course existing in these two resonance structures. If I introduce an electrophile into the system, what can occur is the negative charge that's existing here at this carbon can reach out and grab that electrophile, forming a bond between the carbon and the electrophile. This type of product is called an alpha substituted product. The same type of product can also be generated under acidic conditions. However, the mechanism traversed is a little bit different from that in basic conditions. Under acidic conditions, what occurs is the lone pair electrons up here on this carbonyl oxygen reach up and grab a proton from the acid source. This gives me this intermediate. Then the water byproduct can now strip an alpha hydrogen, thrusting the electrons in here to form a double bond and pushing these electrons up into the oxygen to neutralize its positive charge. This gives me an enol. This is not an enolate, it's an enol. At this stage, if I introduce an electrophile into the system, the lone pairs on this oxygen in the enol can come down and push these pi electrons into the electrophile, effectively forming a bond between the alpha carbon and the electrophile. The oxygen is now positively charged because it thrust its electrons down to form this double bond. So the water will come, remove that hydrogen to neutralize the positive charge, and give me the same product that was formed under the basic conditions, while also regenerating hydronium, which can act as an acid source in the next cycle of this reaction. I want you to once again pay attention to the nuances. Basic conditions and acidic conditions can effectively form the exact same product. However, the mechanisms are slightly different between the two. The first reaction we'll learn here then is the alpha-halogenation of ketones, which has to be done under acidic conditions, not basic conditions, for reasons that I'll explain momentarily. Thus, if I treat a ketone, as shown here in these two examples, with catalytic acid and halogen, such as chlorine, bromine, or iodine, then what will occur is a single one of these protons at the alpha carbon will be removed and replaced with a single one of the halogen atoms thrown into the system. Here's the mechanism of that formation. Once again, the carbonyl oxygen will thrust its lone pairs into the acid to become protonated. The water then removes the alpha hydrogen, to generate this enol. The lone pairs on this oxygen come down, thrust these pi electrons out to grab our halogen atom and place it on the alpha carbon. And then water comes and neutralizes this charge by deprotonating it. This gives me my singly alpha-halogenated product. There's another way of doing the same reaction, and that is to just treat this type of starting material with PBr3 followed by water. This reaction, or way of doing this reaction, is called the Hell-Volhard-Zielinski reaction, which is featured in section 19.6 of your textbook. You should note that we've talked thus far in organic chemistry about a Heck reaction and now a Hell reaction. I think this might be as profane as organic chemistry will get this semester. Now, you heard me mention earlier that you cannot do alpha-halogenation under base-promoted conditions. I'm going to show you why. Under basic conditions, all of the alpha hydrogens end up getting replaced with halogen atom. So what occurs is the base removes a single alpha hydrogen, giving me a negative charge at the alpha carbon. That negative charge reaches out, grabs a halogen to put a single halogen on that alpha carbon. But the problem is that at that stage you can't stop the base from removing the second alpha hydrogen. Thus there's a new negative charge that also gets halogenated. Consequently, you can't run a single monohalogenation at the alpha position under basic conditions. If you want to add a single halogen atom at the alpha position, you have to do it under acidic conditions. Because if you do it under basic conditions, you will completely replace all of the hydrogens on the alpha carbon with halogen atoms. Here is the mechanism of that reaction. I won't address it with excruciating detail, but will instead allow you to look at it for yourselves. This brings us to a useful application of alpha-halogenation. You see, there may be some circumstances in which you actually want to replace all of the alpha hydrogens with halogen atoms. And one of those circumstances is this. It's called the Haloform reaction. It can be summarized in this cool animation that I've assembled for you here. I have to begin with a methyl ketone starting material, and I treat it with hydroxide and excess halogen. This could be chlorine, bromine, or iodine, and then I follow it with acid quench. What this does is it effectively converts that methyl ketone into a carboxylic acid. I have to point out one thing, however. This has to be a CH3. This reaction does not work if it's a CH2 or a CH. You might be inclined to think, why can't a methyl ketone be converted into a carboxylic acid directly? In other words, if I had a methyl ketone and I treated it with lots of hydroxide and heat, the hydroxide, we would assume, would come into the carbonyl, could thrust those electrons up there to give me a tetrahedral intermediate like we've seen so many times. And couldn't that negative charge on the oxygen come down and kick off my CH3 to give me this? Couldn't I run this reaction? I hope you guys are noticing some problems with this. This reaction absolutely would not work, and the reason is because of this stage right here. This minus charge comes down, it is not going to kick off a CH3 minus. It's going to kick off an OH minus. Why? Because OH minus is a much better leaving group than a CH3 minus. Thus, I've written that this step is total crap. So you cannot just take a methyl ketone and stir it with hydroxide and eventually convert it over to a carboxylic acid. That will not happen. And yet somehow the Haloform reaction does successfully convert a methyl ketone into a carboxylic acid. How in the world does that happen? To answer this question, we have to look at the mechanism. So here's the mechanism. I have a methyl ketone, and I've drawn out all three of our hydrogens here. I treat it with base, and instead of going into the carbonyl carbon, this base is going to strip one of the alpha hydrogens, plunge those negative or those electrons into the carbon to give me a negative charge here at the alpha carbon. At this stage, this enolate will search out our halogen. I've shown chlorine here, but this could also be bromine or iodine. It reaches out, grabs one of those halogen atoms, and kicks off the other as a leaving group to give me a single monochlorinated product here. Well, the reaction does not stop here. The hydroxide then strips off a second alpha hydrogen to give me this intermediate. This intermediate then looks at our excess halogen, attacks one of those, kicks off the other, and gives me now a dichlorinated species. What do you think is going to occur here? Well, of course, the hydroxide is going to strip off that third hydrogen, dump the electrons down there, and give me this carbanion intermediate. This carbanion is naturally going to seek out more halogen, and you have to run this with excess halogen, and become now trichlorinated. At this stage, now a hydroxide will come into that carbonyl, pushing the electrons up onto that oxygen to give me this tetrahedral intermediate shown here. Now, this is a huge difference between having a CH3 here. It's got a carbon with 3 chlorines. 3 chlorines. What does that do to this carbon? Well, it makes it so that it's a good leaving group. So when the negative charge on this oxygen collapses back down to reform the double bond, it actually can kick off a carbon instead of kicking off the OH. This gives us this product and this negatively charged carbon. Negatively charged carbon, as I've spoken in the past, is typically not a stable leaving group, but here it is. Why do you think that is? Well, it's stuck to 3 intensely electronegative and withdrawing chlorine atoms. Those chlorine atoms are sucking away and helping stabilize this negative charge by induction. As you might have guessed, this negative charge is going to look over and see this newly formed carboxylic acid and deprotonate it. That forms this carboxylate and this product. This product right here is called chloroform. It is a product that you often will see on TV where people try and hold a rag over a victim's face and make them go unconscious. Chloroform actually does work to do that. And I actually saw it on Peter Jackson's rendition of the new King Kong movie, where Jack Black knocked King Kong unconscious by throwing several bottles of chloroform at his face. I have no idea if that would work with a 100-foot tall ape, but it's nevertheless a compound that you have probably seen on TV. The reason that we have to quench this reaction ultimately with acid is to protonate this carboxylate and get out our carboxylic acid product. Once again, as I've pointed out, this reaction only works if there's a CH3 at the beginning. It does not work if there's just a CH2 or a CH. Why? Because you have to have 3 chlorines on this alpha carbon in order to make it a good enough leaving group to get kicked off in this step. If I start with a CH2, then I can only get 2 chlorines on here, which is not enough electronegative suction to make this carbon a good leaving group. And if I only have a CH, then I can only put 1 chlorine on it. Thus, the Haloform reaction only works if you're starting with a CH3, that is, a methyl ketone. This, I think, is a great place for us to stop. So I will conclude our video presentation here, let you guys take a break, and then encourage you to come back, if you haven't fallen asleep, for our next segment from Chapter 19.